All right, you guys. So today we're gonna go over our atomic spectra lab on Labflow. This is gonna be our little pre-lab section. All right. So flame test and line spectra. All of this is about energy. Just like we learned in chapter 4. Okay. So when atoms absorb energy, they often release that energy as visible light. In this lab, we're going to explore two different approaches to measuring this light. A simple test called a flame test and a more detailed measurement of the specific wavelengths of light at the different elements that they produce. Okay, so aka it just means we're going to be looking at energy flowing through different elements and seeing what happens, and two different forms of energy. Okay, so the flame test. When metal ions are placed in a flame, so we're placing metal what? Metal ions. Not just any metal, it has to be ions. And if we remember, an ion is an atom that has lost or gained electrons. So you're going to put that on a flame and it's going to produce a different color. So using this test, we're going to be able to figure out what color they're producing. So, and it's a good thing to be specific with our colors. We don't want to say just any given color or just be random and say, I kind of look, they all look orange to me, and write orange and all, because you're going to get it wrong because they're not all orange. Okay. If you are colorblind or anything, ask someone to guide you and help you with these. All right, so the first one is lithium. Okay, so my thing is already clicked on lithium, and we can watch this. It turns on, and what kind of colors do you guys notice? What do you guys see? Okay, to me, it has like a reddish pink kind of glow or pinkish red, one of those two. So I'm gonna go ahead and describe mine as pinkish red in color. Okay. Because it's not red and it's not pink. Well, it's kind of like a hot pink, so maybe a hot pink as well. Okay. Now you don't have to describe the tiny blue flame here at the bottom, because they're all going to produce that tiny blue flame. That flame comes from the actual gas that is being burned, so not from the ion, not from the metal that was introduced, but whatever the other substance is, the fuel source. All right, let's look at sodium. Wow, very different, right? Like this one is an obvious yellow color to me. So I would write yellow, and it's a bright yellow. It's not dull or anything. Let's look at potassium. Well, potassium has like an orange and some other sparks to it, like orange and red, right? Kind of looks orange, but it's not, because at the same time it was producing like an orange red glow. Let's see. Let's look at it one more time. Yeah, I would describe it as an orange red, like a blood orange. Oh, perfect. Blood orange / red. Okay. Now, this is what I'm seeing, and this is what my observations of these are. Obviously, maybe you guys could see some other color that I'm not seeing. All right, I'm going to jump around and let's check out one of these. Iron. All right, where's iron? There's iron. Okay. You guys notice there's little sparklets inside of it? So it's like an orange with sparks, right? That's what I saw. I saw orange with yellow sparks inside. Now, the reason I'm detailing all of this with you guys, even though it's quite simple, is because in the lab, some of you guys are just very, very non-descriptive of what you see in your observations. And the main key point of this lab is to be descriptive, is to write all your observations down so you don't miss something. Because a blood orange is going to be different from an orange with yellow sparks inside of it. And if you have an unknown given to you, you have to be able to identify what that unknown is. And if your notes aren't detailed, you're going to fail on that section. So you have to detail your notes. Okay, I will do one more. Let's jump to lead. All right, so here's lead. Ooh, it's like a red, like a very deep red, and it varied in colors, right? So I guess it varied in colors depending on which iron ion we must have had. Or sorry, it was lead ion. Let's see. It went from orange, so a deep orange, to a deep red. So it was very dark red, orange. And that's going to be my description of it. All right, so we've kind of figured this out on the flame test. Now, what kind of heat are we using to produce these colors, to excite our electrons? Because ultimately, all of this, the energy being produced, remember, it's the excitation of electrons when they jump from their ground level to an excited level, right? So let's explain. Actually, I think that's going to be over here. Or yeah, we'll explain that later on in the paper. Okay, so we're done with this section. You guys could do more if you like. I'm going to go ahead and now move on to the line spectra. So this one's going to be a little bit different. Oh, this is what I was going to do right here. That the flame test, you're adding flame, right? Fire as your source of heat to excite the electrons. So fire is used to excite electrons. No, that's not a question that's being asked here. It's just something that I want to show you guys just in case you do get asked something similar to that. Okay, line spectra. Here's my line spectra. Now it wants us to sketch the line spectra of each one of these. Right, so hydrogen is the first one being shown. Let's go ahead and jump to, let's do potassium, because I like the sound of it. Ooh, how pretty. All right, so in this case, we have the electrical charge and gas inside a tube. And this is potassium gas. And the potassium gas and electricity is being shown through a spectrum, right? The spectrum distributes the light, or disperses, it disperses the light. And all the light colors of potassium are visible to us. It gets shown to us. So the electrons are being excited through electricity, right? They're excited through electricity. As the light passes through the prism, we're able to see the colors that they produce through the different wavelengths. Right? And I basically said the same thing in a different format. So hopefully one of those formats you guys understand. All right, so we're going to go ahead and draw our thing of potassium. Let's make sure we're not missing any. Okay, so when I see potassium, I see a yellow on the top all the way down to a purple on the bottom. So I'm going to have my yellow right here. And then make sure when you guys are doing yours that in your descriptions that you're actually putting down the colors. Color coordinate your work, right? Don't just put down lines. If you put down lines, it's going to be incorrect. I don't know what your lines mean if there is no description. So let's say you don't have a yellow color. Write the word yellow right on top of it. It's as simple as that. Right? Next colors we see are about 3 different tones of green, right? Luckily me, I own tons of little markers, so I can actually produce different greens. Okay. And like I said, if you don't have one, just describe it. That's as simple. Describe what it is that you do have. Okay. Oh. Shortly below it, I'm going to have a green color. So this one is like a bright green. Then I have another green. Okay, this came out darker, more darker than I wanted it to. But it's another green, and I'm going to do one more green here. Okay. So these are all greens. Okay, my green lines. And then below my green lines, I'm going to have blue lines. So I have an actual like a baby blue first. Let's see. Okay, so I have like a baby blue. And then from that baby blue, I got like another darker blue. And these blues are very close together. Okay. And I have 1, 2, 3 lines of those lighter color blues. So this is bright blue. And this is like a light blue. And this is just blue. And then what I think I see is a dark blue as well. Okay, so I don't seem to have a dark blue. So I'm just going to take my pen that's supposedly blue, that there, and then say dark blue. Okay. And then finally we have one more at the bottom, and that is like a purplish lilac color. So I'm just going to write purple. All right, and I'm going to verify that I have all the different lines. I have 1, 2, 3, 4, 5, 6, 7, 8, 9 lines. 1, 2, 3, 4, 5, 6, 7, 8, 9 lines. I have all the colors of potassium that are produced through this prism. Okay. So remember, in the prism oh, the word just left my mouth. Um, It spreads the light. Oh man, I'm gonna have to remember. I just said it earlier too. All right, I'm gonna have to remember what it is. But anyways, this prism spreads the light, right? And through that spreading of the light, we're able to see the different colors from the wavelength. So, did we use fire for this? What kind of heat source was used? Well, we used electricity, okay? And the electricity passed through that tube. Right. So I just did one here to give you an example of what I want and what I expect in your guys' lab when it's your turn to do it. Right. Okay, so now I'm on that second page of the worksheet. Okay. So the first question says, compare the appearance of sodium in the flame test and the gas discharge lamp. Do you notice any similarities between them? So the sodium in the flame test and the sodium in the gas discharge lamp. So let's look at the sodium here. Ooh, wow, isn't that pretty? Okay, what do we notice? The gas color inside the discharge tube. The color is yellow. We see a visible yellow color. All right, let's go to the flame test, and we're going to go to sodium. you see that same visible bright yellow color. So in comparing them, we notice that they are both yellow in color. So they both the flame test and the discharge tube for sodium ions are bright yellow in color. Right. That's kind of cool. Actually, I think it was cool. All right, next one. In both of these experiments, atoms absorb energy, then they release it as light. What form of energy do the elements absorb in the flame test? What form of energy do they absorb in the gas lab? Oh, interesting. We kind of already went through that. So let's look. When metal ions are placed in a flame, they produce different colors. So we're using a flame to produce that energy to excite the electrons. And here we're using an electrical current. Now I'm going to use this question as another little teachable moment about to go further into detail about electrons and atoms that are being excited and whatnot. Okay, so what it means to go into excitation, if we recall, N is equal to energy level, right? You can have an electron, so a valence electron, that's an energy level 2, just chilling and hanging out, but then you excite the electron. So I'm going to say this is ground state. Ground state. Ground state means normal, okay? So you excite the electron. Excite it. And we're going to excite it either through flame. So the energy for a flame test was a flame. It was basically fire, right? Fire was the heat source. And so fire is used as a heat source. And this one, electricity. Before I forget to give you guys the answers. All right, so we're going to excite it. So either at fire or at electricity or anything, but there's going to be a change in that state. So now the electron's going to get excited and it's going to jump up, and it could jump up 1 energy level, it could jump up 3. All right, it varies depending on the amount of energy and which electrons we're talking about. So this is the excited state. Okay. Now, when an electron's in the excited state, it is absorbing energy. Okay, so it's taking it in. It's like you just drank yourself 3 espressos and a Red Bull. You just absorb so much different energy and you're like hyped up, right? That's like the electron. It's like super hyped up. It just drank a whole bunch of Red Bulls and it's like, I'm ready. Let's go. It's dancing, everything that you can imagine. That's your electron when it's excited. Now, when it's excited, that's not when you actually see the colors that we're able to see on here, okay? Because it's absorbing that energy, it's taking it in, and that causes it to jump up really high to a different energy level. So when do we see the colors then? As an electron can get excited, it could also fall back down. So we could actually get the same electron and go into the reverse order. So I'm going to write it like this, just so you guys don't get confused. And I didn't put it here because of there's no space. I could have easily just put the arrow here. All right, so this part right here is going backwards. It's going from a high energy state to a low energy state. So this is a high energy, and this is low energy. So what does that mean? Yep, sugar crash. All right, it's done. It was like, whoo, I had so much, now I need to fall asleep. All right, so when this happens, it's no longer absorbing energy, it is releasing energy. So it goes from that high energy known as the excited state back down to the ground state or a lower energy level. Sometimes they don't go back to where they came from. It might go back down to N3 or maybe N4, right? Not exactly N2. So I'm just going to say it lowers down to a low energy level. And when this happens, during the release of this energy, we see light. So this produces visible light. I think this is really cool. Well, if you think about it, your energy has to go somewhere, right? It has to go somewhere. When you're being super excited and whatnot, and you're jumping up and down, you're starting to sweat. So your energy is starting to leave unbeknownst to you. And as that energy is leaving, if we were electrons, we would be able to see that in the form of visible light. Sometimes we could see it like in sweat kind of thing. All right. So visible light is by releasing energy. Okay, so it's releasing energy. Now there's a little bit more that we could show with that, but this is the basics of it, right? All right, let's go ahead and move on. So for hydrogen, we absorb 4 spectral lines, red, light blue, deep blue, and violet, using the equations below. Calculate the frequency and energy for each wave. All right, so it actually even gives us the equation. So all we actually need here is a handy dandy trusty calculator, which I always misplace. Ah, found it. Phew. Right here. Actually, this wasn't my favorite calculator. I left my calculator somewhere, and I was kind of sad, but at least I have one. Okay. So using our handy dandy calculator, we're going to solve. Remember, it's very important to use the correct units. And luckily for us, this worksheet actually tells us to convert from nanometers into meters so that we don't mess things up. Okay. All right, so what is our conversion factor? We know that 1 meter is equal to 10 to the 9th nanometers. Okay, so if I wanted to convert this into meters, I'm going to take this number and divide it by 10 to the 9th, which is the same as 1 times 10 to the 9th. Now I could just move a whole bunch of decimals and everything, so I could take this understood decimal and start moving it 9 places this way, or I could put it in my calculator and let that do the job for me. Okay. 5.56 to the negative 7. Oh, I mean 6.56. All right, so what that means now is I don't have to do this anymore to the rest of these. They're all going to be this number, 4.86 times 10 to the negative 7. 4.34 times 10 to the negative 7, and 4.10 times 10 to the negative 7. All right, if you have any doubts, go ahead and put it in your calculator. Okay, okay. So frequency. In order to find frequency, use with a given wavelength. We're just going to use that equation right there, and the variable. It's already solved for the variable, so that's even cool. So we're going to take the speed of light and divide it by the given wavelength. Okay. So let me actually close that. All right. Okay, So let's take the speed of light, 3 to the 8th power, and we are going to divide it by the wavelength here. Divided by 6.56 to the negative 7th power. Negative 7th power. Okay. I get this huge number, and we already know we don't produce answers like that, right? We don't write that on our paper. So we're given 3 significant figures. I'm going to write down 3 significant figures, and that goes to the 7. There's a 3 next to it, so I'm not going to round up. So that's just going to be 4.57 times 10 to the 14 hertz, or per second. Remember, hertz is the same as 1 over s, which is the same as s to the negative 1. And here all my units are meters. Now, the main reason I didn't write it is because it was already on the top, but I don't want to show you guys bad habits. Write your units down. Okay. All right, let's do another one. 3 to the 8th, which is the speed of light. And if your calculator doesn't have this function right here, it should have a function that reads as like EE, like that, or EXP. So those functions for the exponents for when you're doing scientific notation. Okay. All right, so here I'm going to take that and divide it by 4.86 to the negative 7. And I got 6.17 times 10 to the 14 hertz. Okay. And we could continue doing this all the way through. Well, which, you know, we probably should. It's asking for which one has the lowest energy and whatnot. But you know what? Let's just calculate energy and see what happens. So energy is going to be equal to our frequency times Planck's constant. So I'm going to do this one because the number's already there. I'm going to just multiply that by Planck's constant to negative 34. And I get 4.09 times 10 to the negative 19 joules of energy. And I'm going to do this one because it's already there. So 4.57 to the 14 times 6.63 to the negative 34. And I get 3.03 times 10 to the negative 19. Okay. All right. From there, we could see that the amount of energy has actually increased. Okay, the amount of energy has increased from this one to this one. So from red to light blue. Okay. All right. Let's look at. Let's just go ahead and finish these off. Oops. It's 3 to the 8. 6.91 times 10 to the 14 hertz. Let's go ahead and do the other one. 3 to the 8 divided by 0.1. Okay, we can see that the frequency has drastically increased from red to violet. We have a drastic increase in our frequency. Okay, drastic increase in frequency. Our wavelength became smaller and our frequency became bigger. So wavelength decreased here, but frequency has increased going down. So that tells me that my energy is also going to increase. With that being said, it says in the table above, which line has the lowest energy? Well, that's going to be your top one. So it is red at 656 nanometers has the lowest energy. Which line has the highest energy? Well, I'm going to assume it's this one. Okay, and you guys could finish the math on these two and see if that's true or not. Take this number and multiply it by Planck's constant, and you're going to notice that this number is bigger than this one, and this one's going to be bigger than that one. Okay, so violet at 410 nanometers has the highest energy. All right, you guys, I hope this video is helpful and it helps you guys during your lab, and you guys know kind of what your expectations are when it comes to describing your colors, drawing your line spectras like this one right here, and doing some of that math. All right, ciao.